Okay, so I'm back with a full frame range simulation. So I created this flipbook. It took more or less about an hour. I do have to say that I changed a few parameters. I will go through them in a moment. But notice how we have a nice motion. I have controlled much more the amount of particles that were exploding or just moving out of the group. And let me show you the scene. I did reduce a bit the size of the domain just to optimize a little bit more the scene. I decreased a little bit the size of the emitter just not to get much water out of this channel. In the end, I did increase the resolution to 0.01. The particle separation is lower now. And one thing I also did is I decreased a little bit the initial velocity. Now, the next step is to export the particles and cache this simulation. And not only the particles, in a moment you will see what type of data we're going to export. So I also organized a little bit more the file just to make it cleaner and easier to look at. So I'll go down here below the DOP waterfall and I will add a .io node. And I will fetch the data from my simulation into this node. So the first thing that I'm going to do is I'm going to drag and drop this node here to where the DOP network is. Another thing that I will need is to fetch the actual geometry or the node from the DOP network. So I'm going to dive into the DOP network. I can copy this flip object node just to copy its path. And back in my .io node, just paste that path here. So before we can see anything here, I will choose a preset. So you can find a flip fluid preset, which is very handy. And remember, we talked about this in the introduction. So the first thing I'm going to fetch from this simulation is the geometry or the actual particles. Then I'm going to fetch a VDB. It's a surface. It's a signed distance field called surface. And finally, I'm going to fetch a velocity VDB. So these three components will be very important once we start meshing the water and creating white water if necessary. So let's add a ROP geometry output. And here's something very important. You don't want to cache this raw data that's coming out of the simulation. This will be very heavy and it won't be really optimized. For that reason, there's a very powerful node. It's very important that you use this node. It's called Fluid Compress. And again, I recommend you use it every time you're caching your flip simulations. So let's connect this to our .io. And probably the only important thing that you need to take care of is the particle separation. Usually this needs to match whatever you have in your flip simulation. So look for the particle separation here on your flip object. You can copy this parameter and channel reference that into the particle separation of the fluid compress. So right click and paste relative references. So the rest is pretty much fine. You won't really need to change these parameters. Notice that some of the parameters will be deleted, and here you can decide which of these you can keep. I personally rather have more than less, so I won't touch these parameters. And cache, I'm going to name this ROP output as waterfall sim. And here under the ROP geometry node, I'm going to change a few things. First of all, I don't want a single frame cache. I want the entire frame range to be cached. And of course, another very important thing is the name of the file and where I want to save it. So I will save the file to the geo folder. Inside this folder, I will generate another folder with the name of this node, waterfall sim. And for that, I'm going to use the $OS variable. And this is a variable we've used before as well. So this variable will take this name, the name of the node, and replace it here. So the name of the file again will be the name of the node, waterfall sim, with the frame number. And I will only add a number 4 to generate a padding of 4 numbers here. And make sure the extension is .bgeo.sc. And this is all we need to start caching our sim. At this point, you would only click Save to Disk. I have done it already, and a very important thing is that this flipbook that you just saw was simulated with a point separation of 0.01. So depending on how fast is your machine or how much disk space you have in your computer, you may want to lower the resolution, or in this case, increase the point separation. But I know for a fact that the higher the resolution, the nicer the simulation will look, and especially the meshing will have much more detail. So let's go with this. Cache your simulation, and we'll be back in a moment.